Right, let's have a little look at this intro for the remainder and factor theorems. I've written down the remainder theorem here as a given. When f of x is divided by x minus a, the remainder is r say is f of a. And the factor theorem, if f of a is 0, then x minus a is a factor of f of x. So for example, then if we put in 2 here, f of 2 or f of minus 2, let's do f of minus 2, shall we? So let's work at f of minus 2 in this case. So it's minus the something cubed, minus 2 times the something squared, minus 5 times the something plus 6. The input is minus 2. So what do we get? We get minus 8 here, because it's minus 2 cubed. This is a plus, times a minus is a minus. This is 4 times 2 is 8. Minus times a minus is a plus. 5 2 is a 10, plus 6. You've got 16 takes 16, which is 0. So that tells you, in this case, that x minus this value, so it'd be minus 2, is a factor. And that's by the factor theorem. On the other hand, if we did f2, let's do f2 then. So I'm going to scratch this now and just put 2 in. So we're okay with that. Oh, I'll leave it there. F of 2, on the other hand, is equal to 2 cubed, yeah, the input is 2, minus 2 times 2 squared, minus 5 times 2 plus 6, equals 8 minus 8, minus 10, plus 6. Let's just check that. 8, yeah, 2 cubed is 8. 4 2s are 8 with a minus. Minus 10 plus 6, what do we get? Minus 10 plus 6, these cancel. Minus 10 plus 6 is minus 4. So remainder r equals, and we're told the remainder is f of a, f of 2 equals minus 4. So there's the actual using them in practice. That's how they're used. Once we know x plus 2 is a factor, then we can divide that into that. So just a little, let's just be happy that we can see why that's the case then. So I'm just going to get rid of this now, and then we'll just have a little look at why, or some of the reasons why anyway, at least. So let's have a go here then. So we said when we divided it by x minus 2, it had a remainder of minus 4, I think we said, didn't we? So if I said, if you have x cubed minus 2x squared minus 5x plus 6, that can be equal to, then we'll have the x minus 2, right? Okay, and that would be times a quotient of x. That goes into that so many x's, right? Which we can call a q of x, a quotient. Okay, but it has a remainder. Now the thing about the remainder, for it to be a proper fraction, it must be of 1 degree less than this. This is of degree 1, so it must be of degree 0. So this must be a constant, which we'll call the remainder term. And that remainder is just a fixed constant because of the fact that this is a linear function here. So I hope you can see that the remainder, when you do long division, has to be 1 degree less than this to have a proper fraction, which we can do that as a process. And because it's 1 degree less than this, and this is of order 1, the order of this must be 0. In effect, that means that's a constant. All right. So that's a little bit of the bookwork behind it then. So if that's a constant, if we put in 2 here, that will go to 0. So that implies, if we input the value 2, you get 8 minus 8, as we said before, minus 10 plus 6. Then you put 2 in there, you'll get a 0 times qx, which is 0 plus r. So that implies, reading from right to left, that r is equal to 0 minus 10 plus 6 is minus 4. But we started by inputting the value 2, didn't we? So this is f of 2. So that's a little bit behind the reasoning, using the properties of long division, where we get this property here of the remainder theorem. Okay, and of course if the remainder is 0, then we know it's a factor, because if it has no remainder, then this thing has gone into this cubic a whole number of times, qx. Now how do we find qx? Well, there's two methods we can employ. We can do long division, So we know one of the numbers is, let's just get rid of this now. We know one of the, we know x plus 2 is a factor, don't we? So let's just write down here, x plus 2 is a factor. We did that before at the outset of f of x. Now how do we find the other terms? Well, here we can just do it by inspection. So I'll do it by inspection first, and then I'll do it by the slightly more long-winded method of long division, just as quickly as I can. So let's divide, let's see how many times this goes in. I'm doing a long division in a minute, but I'm going to just do it by inspection first. So this goes into the x cubed how many times, which is what I need to put here. So let's look at that then and see how we obtain this quadratic here. Well, first of all, you look at the dominant term, the cube, and x, and you ask yourself what needs to go here for it to be an x cubed. Well, you're going to need an x squared. So you multiply out and you'll get your x squared done. Now the next, that will generate 2x squareds. We've got minus 2x squareds, haven't we? So we need a minus 4x to go with that x to make minus 4x squareds. So the total number of x squareds from this expansion then will be the 2x squared here and the minus 4x squareds, which we just put in, and that makes a total of minus 2x squareds. But we'll get out from that, if we think about it, minus 8x from here, won't we? So how many? We need minus 5, so we need to put in a plus 3 so that we get a plus 3x here. So how many x's? Let's just check that then. We'll get minus 8x here, and plus 3x will give us minus 5x. And then you'll notice that the 3 times 2, because this was a factor and we knew it to be a factor, the 3 times 2 product automatically gives the number at the end 6, so that fits. So that's a little check as well, isn't it? So you can see that you can divide that very easily by inspection. You can divide this thing into this thing by that process, and it goes in that many times. And then it's just a simple matter of factorizing this bracket here. We've got x squared, so we could write xx. We've got 3, so it has to be 3 and a 1 if it factorizes easily. And then we've got minus, so it looks like a minus and a minus, doesn't it? So x squared minus 3x minus 1x is minus 4, and then plus 3. So you could let that equal 0, couldn't you? And then you could find the roots as well. But this is the process of factorization. Now I said briefly I'd mention about long division, because sometimes we can do long division if we prefer. If we're not happy with that process there. It doesn't take an awful lot longer, but maybe slightly longer. So let's have a little look at that then. So we want to do long division then. So I'll just remind you of the process of long division. So we're trying to work out x plus 2 is a factor. So we want to know how many times that goes into this quadratic. And see if we can generate the same quadratic. So you look at the dominant terms, how many x's go into x cubed? Well, that'll be x squared. Multiply through as you would do normally with long division. So x cubed and then plus 2x squared. Then you take them away. So this disappears. This take away that will be minus 2x squared. Take away 2x squared is minus 4x squareds. Then you've got minus 5x take nothing, which is minus 5x. 6 take nothing is plus 6. Then you look at the dominant terms and repeat the same process. How many of these go into this? Minus 4x. Agreed? That will generate minus 4x squareds here. Then you'll get a minus times a plus is a minus 8x. So let's take them away then. This take that will cancel, that's why we're doing it. Minus 5 take away minus 8 is plus 8x. 8x take 5x is 3x. We've got a 6 take nothing here, so that's plus 6. And then the last step, how many times does x go into 3x? Well, it'll be plus 3. And then you'll get, multiply through, you get 3x. And then you get 3 2s is 6. Take them away, and you do get your 0. So we can see that we can write the product, once again, of x squared minus 4x plus 3. It takes marginally longer. And then you can factorize as we did before, x plus 2, and this factorized into x minus 3, x minus 1, wasn't it? Okay, so you pay your money, you take your choice in terms of what you prefer doing. I quite like the first method because it is slightly quicker, I think, but this is a good fallback method if ever you get confused by the other process. So it's good to have both tools in the tool bag, so to speak. Okay, then I think that's enough to say about this section. If I think of anything else, I'll put it in the long click. But that's all I'd like to say for now. So all the best in this section. Hope you get something from it. Cheers.